Welcome to the second video. So in the last video we have seen what is a natural number p1 as axioms, and we extend it till to uh, r by finding this there is a gap between rational numbers, mainly x square equal to p, that is a uh, not solvable. Therefore there are some gaps. We come to know that there are some gaps, and we named that gaps as irrationals. So, and we joined that rationals and irrationals, and we call the set as real numbers. And in general, in generally we defined in one what is an ordered set, that is, what is ordered set, and we define in an ordered set we defined what is upper bounds and lower bounds, and supremum and infimum, and we have seen some examples of it. Set which is, and if a set is having upper bounds, then its set is bounded above, and if a set has a lower bound, then the set is bounded below. If a set has both upper bound and lower bound, then the set is bounded. And we also calculated some, we have seen some examples of set having lower bounds, and having no upper bound. Okay, so what happens if the set has two supremum? Okay, let E be a, so let E be a subset of an S, where S is an ordered set. Suppose this E has a two supremum. Say alpha 1 is a supremum of E over Q, and say alpha 2 is also supremum of E over, sorry, not E over Q, over S. E over, and that means, suppose E has two supremum, say alpha 1 and alpha 2. Now what's this alpha 1? Alpha was is an upper bound of E. Moreover, this alpha 1 is the least upper bound of E. What do you know about alpha 2? Alpha 2 is also an upper bound of E, and alpha 2 is the least upper bound of E. Now observe, alpha 1 is an upper bound, least upper bound. Alpha 1 is a, okay, is a least upper bound, and alpha 2 is an upper bound. Both are upper bound or least upper bound. Now consider alpha 1 as a least, assume till this, just considering alpha 2 as a upper bound, we get alpha 1 is less than or equal to alpha 2, because alpha 1 is a least upper bound, alpha 2 is an upper bound. Now in the reverse order, alpha 2 is a least upper bound, and alpha 1 is an upper bound. Now this too implies alpha 2 is less than or equal to alpha 1. That is, alpha 2 is a least upper bound and alpha 1 is an upper bound. By treating alpha 1 as just an upper bound, therefore we get alpha 1 equal to alpha 2. Similarly, this is, if the supremum exists, then the supremum is unique. In the similar way, if the infimum exists, then the infimum must be unique. Okay. Now so in this problem we said if the supremum exists, then they are unique. That means there need not be supremum exist always. So for a set, then supremum need not be exist always. Okay, now take let S is equal to Q. And A is a subset of Q, is given by set of all P belongs to Q, such that P greater than 0, and P square is less than 2. And B is a set of all Q belongs to Q such that Q greater than 0, and Q square is greater than 2. Now clearly A and B are two subsets of Q, and is a subset of Q. Now first we observe that this A has no largest element. We shall show that this A has no largest element, and this B has no smallest element. Now to show A has has no largest element. And what is the meaning of that? A has no largest element. For any p belongs to A, for any p belongs to A, there exists some q belongs to A such that p is less than q. This says if you take any element in this A, if you take any element in this A, you get an element greater than that. Therefore, A has no largest element. A has no largest element. Similarly, B has no smallest element. B has no smallest element. We shall prove that B has no smallest element. Now that means for any q belongs to B, there exists p belongs to A such that my p is less than q. Say for any q belongs to B, there exists p belongs to B such that P belongs to B such that P is less than Q. B is less than Q. That means this B has no smallest element. So to prove this, let P belongs to Q. Consider a rational number P with P greater than 0. P greater than 0. Now consider Q is equal to P minus P square minus 2 divided by P plus 2. P plus 2. Now by solving this we get this is equal to 2 times, so just multiplying we get it is common, making common denominator, we get it is 2p plus 2 divided by p plus 2. Now from this q square minus 2 is nothing but 2p plus 2 divided by p plus 2 minus 2. This is we get it is 2 into p square minus 2 divided by p plus 2 whole square. Now first, now as we mentioned in the beginning, we shall prove that my A has no largest element and B has no smallest element. Now to show A has no largest element, let if P belongs to A, then from the definition of A we know that P is greater than 0 and P square is less than 2. This implies P square minus 2 is less than 0. Now P greater than 0. Now using this relation P greater than 0, we get P greater than 0, therefore Q is also greater than 0. This implies Q is greater than 0. Using these two relation, we get Q is greater than 0. Now using this relation, we get q square minus 2. Now observe p square minus 2 is less than 0. This one is less than 0, but 2 by p plus 2 divided by p plus 2 whole square is greater than 0. Therefore this number is less than 0. That means we got q belongs to A. Now because see, q is clearly a rational number and q is greater than 0, q square is less than 2. Now using this again, now wait now we have q is equal to p minus p square by 2. That is q is equal to p minus p square minus 2 divided by p plus 2. Yes, p minus p square. Yeah. Now we know that this, now p square by 2 is p square minus 2 is less than 0 and p plus 2 is greater than 0. Therefore this is less than 0. Now p is greater than 0, q is greater than, so we are subtracting a number is less than 0 from P to get Q. Therefore my Q has to be greater than P, because this will be P minus of a number, so this gives my Q is greater than P. So therefore, for a P belongs to A, we got a Q greater than 0, and Q, a rational number Q greater than 0, Q square is less than 2, and Q is greater than P. This implies A has no largest element, Okay. Now in the similar, if B belongs to B with the P greater than P minus 2 is greater than 0, because P square is greater than 2, now using this relation, wait, wait, okay. Yes. Now P square minus 2 is greater than 0. This whole term is greater than 0, implies Q square minus 2 is greater than 0. Now Q belongs to Q with Q greater than 0, and Q square minus 2 is greater than 0, that is Q square is greater than 2. Q square is greater than 2. Now using this relation, now P square minus 2 divided by P plus 2 is greater than 0. So we are subtracting this number from P to get Q, to get Q. Therefore my Q must be less than P. Q is less than P. So for a P belongs to B, we got a Q belongs to so this implies Q belongs to B. So for a P belongs to B, we got a Q belongs to B, that Q is less than P. Therefore my B has no smallest element. Now so we have shown that this A that's a subset of Q, and this B is a subset of Q, such that A has no largest element and B has no smallest element. Next we shall show that this B is the set of all upper bounds of A. B is the set of all upper bounds of A. B is the set of all upper bounds of A. That means we shall show that B is the B is the set of all upper bounds of A in Q. That means we need to show that every element of B is an upper bound of A, and if A has any upper bound, it's an element of B. That means we need to show in two directions. That is, every element of B is an upper bound of A in Q, and we need to show any upper bound. We should write in the shorter form UB for upper bound. Any upper bound of A in Q is an element of B. So first we shall show that B is the set of all upper. First we shall show that every element of B is an upper bound of A in Q. Now let P belongs to B. Now to show P is an upper bound of A, we need to show that P is greater than or equal to Q for all Q belongs to A. To show P is greater than or equal to Q for all Q belongs to A. Suppose not. That means P is less than Q. Then now P is an element from B. That is, suppose not, where Q belongs to B. Now q belongs to A, q belongs to A. Now P is an element in B, P is an element in B, therefore P greater than 0. Now if I multiply this relation by P, we get P square is less than P into Q. Similarly, this q belongs to A implies q is also greater than 0. Multiply this q to this relation, we get P into Q is less than Q square. Now combining this, we get P square is less than Q square. P square is less than Q square. But now Q is an element in A implies my Q square is less than 2, and P is an element in B implies P square is greater than 2. Now combining this one and this one, we get that is P square greater than 2 and Q square is less than 2 implies Q square is less than P square. Q square is less than P square, and we get here we have P square is less than Q square, here we have Q square is less than V. It's not possible, and this is wrong because we assumed that P is less than Q for some Q belongs to A. Therefore it is wrong. Therefore P must be greater than or equal to Q for every Q belongs to A. Therefore P is a upper bound. Therefore P is an upper bound of A in Q. Therefore every element of B is an upper bound of A in Q. Now we shall show that any upper bound of A is an element of B. Any upper bound is an element of B. Now let C be any upper bound, BC be any upper bound of A in Q. Now what is the meaning C is an upper bound of A in Q? C is greater than or equal to P for all P belongs to A. C is greater than or equal to P for all P belongs to A. Now clearly C is an element of Q. Yes, C is an element of Q. Now since P belongs to A, P is always greater than 0. P is always greater than 0. Therefore C is also greater than 0. P is also greater than 0. Now we need to show that every upper bound of A is an element of B. That means we need to show that C is every upper bound of A is an element of B. That means C is an upper bound, we need to show this C is an element of B. Now to have it's an element of B, we need to have C is a rational number greater than 0 and C square is, and we need to have to show this C square must be greater than 2. Suppose not, then this C square will be less than or equal to 2 and C square is not equal to 2. Because now this C is an element in Q, implies C square equal to 2. It is not possible. We have seen this. Not possible. Therefore C square must be less than 2. C square is less than 2. Now observe, C belongs to Q, C greater than 0 and C square is less than 2. This implies my C belongs to A. C belongs to A. Now, whenever C belongs to A, since A has no largest element, there exists Q belongs to A such that C is less than Q. C is less than Q. But what we have assumed, well, C is an upper bound of A. Therefore, C must be greater than every element of A. But we got C is less than an element of A. It is a contradiction. Therefore my C square must be greater than 2. C square must be greater than 2. Hence we proved that every element of B is an upper bound of A, and any upper bound of A is an element of B. Every element of B is an upper bound of A, and every element of B is an upper bound of A, and any upper bound of A is an element of B. Now moving further, The similar way, in the similar way, we are showing that now. Observe my b, a is nothing but, so just recall the set once again. A is equal to p belongs to q such that p greater than 0, p square is less than 2, and we have b is equal to, that is nothing but q belongs to q such that q greater than 0 and q square is greater than 2. Now we shown that b is the set of all upper bounds of a. Now take any rational number r belongs to q such that r less than 0, that's a negative rational number. Then this rational number is always, because elements in b is always greater than q for all q belongs to b. Every rational number, every negative rational number is a every negative rational number is a lower bound of b. Therefore, if I take p is equal to set of all r belongs to q such that r less than or equal to 0, you can see 0 is also lower bound. This is the lower bounds. Is a set of all. This set is a set of all lower bounds. Not set of this set contains some lower bounds of b. This set contains some lower bounds of b. Now we shall show that a union p. Let's take this set as yes. A union p is the set of all lower bounds. Is the set of all lower bounds of b in q. Now to show, as we did in the previous case, to show this set S is a set of all lower bound, we need to show that every element of S is a lower bound of b, and any lower bound of b is an element of S. Now take an element of S. Let S belongs to S. Since S is equal to A union P, S is in A or S is in P. Now S cannot be in both, because any element in element in A are greater than 0 and element in P are less than or equal to 0. Therefore S cannot be in both the set. Therefore, suppose the case 1, suppose S is in P, then clearly S is less than or equal to 0, but element in B is always greater than 0 for all q. Therefore, every element of P, as we seen in here, every element of P is a lower bound. Now the second case. Suppose S is in A, we need to show that S is less than or equal to every element of A. That is to show S is less than or equal to Q for all Q belongs to B. To show. Suppose not. That means S is greater than Q. Now since S is in A, we have S is greater than 0. So multiplying this relation, we get S square is greater than S into Q. Now Q belongs to B implies Q is also greater than 0. So again multiplying this relation, we get S into Q is greater than Q square. Now combining this, we get S square is greater than Q square. Now, but S belongs to A implies S square is less than 2, and Q belongs to B implies Q square is greater than 2. Now these two together implies my S square is less than Q square. Here we have S square is greater than Q square. Here we have S square is less than square. They are not possible. It is not possible. Together it is not possible. This is not possible because we assumed that S is greater than Q. Therefore, this is not true. Therefore, S must be less than or equal to Q. S must be less than or equal to Q for all Q belongs to B. Now S is an element of S is less than or equal to Q for all Q belongs to B. Therefore, this S is a This yes is a lower bound of B. Therefore, this is every element of yes. Every element of yes is a lower bound of B. Now we need to show that every lower bound of B is an element of yes. Is an element of yes. Now take a lower bound. Take a lower bound. Let L let L be the let L be a lower bound of B in yes. That means L is less than or equal to B, as L is less than or equal to say P for all P belongs to B. That means L is less than or equal to P for all P belongs to B. Now elements in P are greater than 0 and L is less than or equal to P. L is less than or equal to P. Therefore, now now L is a lower bound of B in B. Yes, S is nothing but here Q. S is nothing but here Q. Now that means L belongs to Q. Now we shall go with the two cases. Suppose L is less than or equal to 0. Suppose L is less than or equal to 0. Clearly it's a lower bound, and this implies L belongs to P, implies L belongs to yes. L belongs to yes. Suppose L is greater than 0. Suppose L is greater than 0. Now we shall show that this L belongs to yes. Now clearly L is in Q and L is greater than 0. Now suppose now since L is greater than 0, L is not in P. Therefore we need to we need to show L belongs to yes. We need to show L belongs to A. Now to show L belongs to A, the L must be greater than 0. Yeah, it's clearly L square must be less than 2. We need to show L square is to show this. We need to show that is to show L square is less than 2. Suppose not, this is not. That means L square is greater than 2. L square is greater than 2. Now wait a second. Now this is now this is L belongs to Q, L greater than 0 and L square is greater than 2, implies L belongs to B. L belongs to B. Now whenever we get an element in free, there exists some Q belongs to B such that L is uh, greater than Q. L is greater than Q because B has no smallest element. Now L is an element of B, so there exists an element in Q such that Q is less than or equal to Q is less than B because B has no smallest element. Now what we have assumed L is a lower bound of B. That means L is less than or equal to it's given L is less than or equal to every element of B, but we got L is greater than an element of B. It is not possible. This is not possible because we assumed that L square is greater than 2. Therefore L square must be less than 2. Now L is a rational number greater than 0. L square is less than 2, implies my L must be belongs to A. This implies L belongs to yes. Therefore we every lower bound of B in Q is an element of yes. Therefore S is the set of all lower bounds. S is the set of all lower bound of B in Q. Now so we started with the set Q and the subset A B. We started with the we uh, started with the Q, and A and B are two subset of Q, such that B is the set of all upper bounds of A and elements in A are the lower bounds of B. So observe, B is the set of all upper bounds of A and elements in A are the lower bounds of B. I'm not saying every A is the set of all lower bound. Every element in A is the lower bound of B. Now we shall prove that we shall show that A now this A B is the set of all upper bounds of A. B is the set of all upper bounds of A, but therefore A is bounded above. Now A is the lower bound of B, therefore B is bounded below. Now suppose my A has supremum. Say let alpha is equal to supremum of A over Q. Supremum of A over Q. Suppose alpha is equal to supremum of A over Q. Now this implies alpha is an upper bound of A in Q. Now alpha is the supremum of A over Q, and therefore alpha is an upper bound of A over Q, and we know that B is the set of all upper bounds of A. B is the set of all upper bounds of A. This implies my alpha belongs to B. Now in B we have a property, B has no smallest element. That means there exists P belongs to B such that P is less than alpha. Now P belongs to B. Implies P is a upper bound. It's an upper bound of P is an upper bound of A. Now P is an upper bound of A, and alpha is the supremum of A. That means it's the least upper bound of A. Therefore, their relation must be alpha must be less than or equal to P, but we have P is less than or equal to alpha. These two are not possible. Therefore, A has no supremum. A has no supremum. In the similar way, B is now bounded below. Suppose B have infimum. Say beta is equal to infimum of B over Q. Now this implies this beta is a lower bound. It's a lower bound of B. Now whenever B has a lower bound, now we know that B is greater than or equal to 0, or B is, that means this B is in, it's a lower bound. Now set of all lower bounds of B is nothing but, yes, that is A union P. That means either B belongs to A or beta. Beta belongs to A or beta belongs to B, but beta cannot be in P because elements in A are greater than 0, and elements in P are less than or equal to 0, and beta is a lower bound. Moreover, it's the infimum. It means it's the greatest lower bound. Therefore, beta must be in A. Now A has a property that A has no largest element. This implies there exists some P belongs to A such that beta is less than P. Now P belongs to A. We know that every element of A is a lower bound of B. And beta is an infimum. So beta is infimum. That means beta must be greatest lower bound. Therefore, beta must be greater than or equal to any lower bound. Beta is greater than or equal to any lower bound. Here it is P. Here we have beta less than P. Here we have beta is greater than or equal to P. they are not possible together. That this therefore B has no lower bound. B has no infimum. Therefore, thus we got a set. Thus we got a set Q. In set Q, we got two sets A and B, such that A has upper bounds, B has lower bounds. Repeating, A has upper bounds, B has lower bounds, but A has no supremum, B has no infimum. Therefore, a set which is bounded below need not have infimum always. Similarly, a set bounded above need not have supremum always. Thank you.